two content. Okay, yeah. Here I just show you how to use this powerful tool to compare two growth functions. One grows faster than the other. Yeah. All right. All right, so the method two, yeah, because we compare method two with method one, yeah. When we use the L'Hopital's rule, the basic the method is this. Yeah. We need to find the limit of ratio of two functions, two original functions. But usually that ratio sometimes hard to find directly. The limit hard to find directly. But based on the L'Hopital's rule, we can take the derivatives of those two functions. Yeah. So you do not compare two original functions, you compare their derivatives. And we hope when we work on the derivatives, we can find the limit easier. Yeah. So that's the main step we need to use here. Yeah. Derivatives. Yeah. Okay, yeah. So that's a simple idea. But before you apply it, you need to check if it's legal to apply the L'Hopital's rule. You need to check the condition. It may not be legal. You may apply in the wrong way. Now, so what's the right way? You need to make sure you apply on indeterminate form. Indeterminate form. Infinity over infinity. Yeah? Two functions, both functions go to infinity. That's we call infinity over infinity form. Okay, it's the indeterminate. Yeah, because it could be anything. That ratio could be anything. It's not determined. Not determinate. Okay, could be anything. Okay. Could be zero, could be constant, could be infinity, could be anything. That form. Okay, yeah. So we call it indeterminate form. Another possible indeterminate 0 over 0. But here, because we use it in our algorithms, we do not have second indeterminate. In math, you may have a second indeterminate form. But in our algorithms, we only have the first indeterminate. Because our growth functions usually go to infinity. All right. Yeah. But in math, actually, there are a few more indeterminate forms. Yeah, but here for example, 1 to the infinity. That's another indeterminate form. Yeah, yeah. Infinity to the zeros, right? Indeterminate. Okay. In math, there are many different indeterminate forms, but for our algorithm, the only one you need is this one. And also, yeah, for example, times 0. Okay, could be anything. Indeterminate could be anything. Okay, yeah. All right. Now, so let's look at first. We know this is indeterminate form, a to the u. The numerator function goes to infinity, and denominator function also goes to infinity. So no problem. It is an indeterminate form. So we can apply L'Hopital's rule here. Okay, yeah. Then we take the derivatives. The numerator, denominator, derivative of u, 1. That's easy. Derivative of u is 1. Yeah, I hope you can still remember the simple one. But exponential function a little harder, so we can find its formula somewhere. Okay, yeah. on web or in your textbook, yeah, old textbook, yeah, that is natural log of A times A to the U. Yeah. That function, yeah. Natural log of A. Okay, yeah. All right. So now after you take the derivatives, then you can get the answer easily, right? Denominator just 1, very simple, yeah. But the numerator in the parentheses, it's a constant. Natural log of A, it's a constant. A to the U, that function should go to infinity. That function, when U goes to infinity, that function also goes to infinity. So the answer is infinity. Infinity over 1, so that's also infinity. Yep. So you can see we get, this is rigorous proof. Yeah. When U goes to infinity, A to the U over U goes to infinity. Rigorous proof. Yeah. Okay, yeah. All right. Yeah, so this is one simple example. We use L'Hopital's rule to compare two growth functions. All right. Yeah, but here, yeah, we need to make sure our A is greater than 1. Then natural log of A is positive. Yeah. Natural log of A is a positive number. Yeah. All right, yeah. Yeah, but there is another issue here. Yeah. So I try to make sure all our logical reasoning rigorous here, because you take derivatives of two growth functions. How do you know you can take derivatives of two growth functions? That step, you need to make sure it's legal, right? So then the next step, I try to address this question. When you take derivatives, you need to make sure that step is legal. Okay, yeah, here. Why you say sometimes legal, sometimes illegal? Because you need to make sure the functions that you take derivatives must have continuous variables. Continuous variables. The variable change continuously, okay? Not taking random value, not taking discrete values, okay? Yeah. So here, let me show you another example. So what's the difference between discrete variables and continuous variables? Look at this ratio of two functions, n over log n. We know n can only take discrete values, right? 1, 2, 3, 4, discrete values. N is not a continuous variable. N is not continuous variable. Okay? So it's a discrete variable. Discrete variable, a function using discrete variable, you cannot take derivative. It's illegal. It's illegal. Okay? So we need to make this step rigorous. Yeah? We need to make this step rigorous. Okay? Unfortunately, in our textbook, this step is not rigorous. It just takes derivative on random variable, on discrete variables. Okay, not rigorous. Yeah. So, all right. So let me show you how to make it rigorous. The question.
Maybe it's obvious for people, but how come in the previous iteration when we were looking at AU over U, U wasn't considered continuous or is considered?
Yeah, good question. Actually, yeah. So here, the question, yeah. So actually, if we go back, connect to the original functions, they're not continuous. Okay, not continuous, also discrete. Yeah. But we can, there is option we can think of. We can do this problem on continuous variable. Then we go back. All right. So that here, the way we do, I show you here. After I show you the way here, then you use the same way, going back. Yeah. Actually, that's a very good question. Yeah. Actually, here we bypass that rigorous step. We bypass. Okay. Yeah. But here we bring it back. Yeah. We skip that step. Now we bring it back. Yeah. All right. We know discrete variables. Now, can we write their continuous counterparts? Continuous, yeah, the function, but we use continuous variable. They're corresponding continuous functions. Okay, yeah. So we consider, how about we consider this new limit? This time we assume x continuous variable. Yeah. Two functions. So here you can see they have the same form, but the values, one discrete values, another continuous values. We have them. So here we consider. How about that? Our goal, we need to find that. Okay. Here we change our problem slightly. We do not say they are the same. Okay. But we change the problem slightly. Can we modify the problem to this one? Calculate this limit. All of that. We just calculate this limit. But when we calculate the limit, our x goes to infinity, x changes continuous. So it's a continuous function. Here we're not allowed to make any change continuous, only discrete values. So that's the difference. Here we allow continuous, change continuous, right? You can treat as two different questions, but they're closely related. All right, but good thing is you can take derivatives. Because we use continuous variables, we are allowed to take derivatives. Derivatives are well defined. For discrete derivative is undefined. You cannot define derivatives. Undefined.
So if we were like given this in a homework problem and we ended up with the equation on the left and it said, okay, instead let's consider this so we can solve this.
Yes. Okay. Solve this, then you can answer and go back. Go back. Okay. All right. But I will explain why we can go back. Okay. Another tricky step. Yeah. Hard to understand. All right. Now we consider this closely related question. We know it's different from the original one. Yeah. So this time we are allowed to use the L'Hopital's rule. Okay. Limit numerator, it's 1. Okay. Limit of numerator is 1. Let me review a little bit. Yeah. If you ask me why 1, the numerator we can consider we have a power function. Power function, x to the n, that's a power function. Okay. For the power function, it's derivative. Yeah, this prime means derivative. Okay, the prime derivative. The formula is n times x to the n minus 1. Okay, this is the derivative formula for the power function. Any n. Okay, yeah, any n. Yeah. All right. Here, n equals 1, x equals 1 times x to the 0, so that's 1. Yeah. Power function, derivative. All right. Denominator, log base a, let's assume log base a, 1 over natural log, bracket, natural log times x. That's the formula, derivative of log formula. Okay? Yeah. After simplification, okay, yeah. Reciprocal, yeah. Natural log of A constant times variable x, but x goes to infinity. This is a positive constant. Yeah. Because this natural log of A with A greater than 1, it's a positive constant number. Okay? Yeah. So the limit is infinity. This, by applying L'Hopital's rule, we found this limit, x version, this limit is infinity. Okay, all right. Then we go back to original question. We find the limit is infinity. We could go back to our original question. We say that limit equals equals infinity. That limit equals infinity. Why? Yeah. Let me explain why. Why we can go back? Okay. Why we can go back? Okay. It's legal. It's rigorous. The reason is by the definition of limit. By the definition of limit. So here we need to recall the definition of limit. Here, this limit, all right? This limit. Now you agree. The first thing you agree, this limit equals infinity. No problem, right? By L'Hopital's rule, it's rigorous. Okay? So this limit equals 0. When x approaches to infinity, this limit equals infinity. The question is, what do you mean x approaches infinity? X approaches infinity. What I mean, my question here is, in what way x approaches infinity? Approaching infinity, there is many different ways, right? Yeah. So here my question is, here, let me draw number axis. This is number axis. This number axis goes to infinity, right? Yeah. But our x approaches infinity. We take a sequence of x values approaches to infinity, going along that infinity direction, goes to infinity. Do we have any restriction on x? What kind of values we can take to go to infinity? How to go to infinity? Do we have that information? No, right? No restriction. That means you can take arbitrary way. Okay? It's correct. When x goes to infinity, in arbitrary way, goes to infinity, always correct. Okay? Yeah, x goes to infinity. So you can take, let's select x values goes to infinity. Okay? X 1 square, 2 square, can we take it this way? 3 square, n square goes to infinity. Let's go to infinity, right? Yeah. Can we take 1, 3, 5, all the numbers go to infinity, 2n minus 1 to infinity, right? Can we take even numbers to infinity, 2, 4, 6, 2n to infinity? All legal, right? Then, how about we take a special discrete values, go to infinity? That's 1, 2, 3, to n. When we take this sequence, is it we recover to the original question? Goes to infinity, right? We just take special x values. Yeah. So we do not apply L'Hopital's rule on the original ratio of group functions. We apply here, it's legal. After we get the result, we interpret it. Yeah. Because by the definition of limit, we can take x values in any way that approaches to infinity, all legal. How about we just take the special x values, discrete values? Okay? Yeah. If we take special X value, that's exactly our original limit form. Yeah, so we get around it. Yeah. It's legal. Yeah. And we didn't apply Lopitas rule to discrete variable functions. We didn't do it. We didn't apply directly. And we apply in their continuous counterparts. No problem, right? Yeah, no problem. Rigorous. Yeah. Yeah. All right. Try to understand. Yeah. Yeah. With that, now we have no problem. Later, yeah, as you said, when you have discrete ratio function ratio, you write this version, apply L'Hopital's rule, get an answer, then you come back. That's perfect. Yeah. That's perfect. Yeah.
So the limit of a natural log of A, that one goes to infinity, right?
Limit. Next. Yeah. This is constant. Constant time, this is infinity. Yeah. This A never changes. Yeah.
Okay.
A, positive, A greater than 1, so this is greater than 0, but we fix it. Then we change this number.
Okay, that makes sense.
Yeah.
Okay. The A was throwing one.
Yeah. Even this number very small, doesn't matter. 0.0001, but this X space could be very large.
Okay, gotcha.
All right, so we complete our part B. Yeah. All right, so the conclusion, yeah. So hope you can see it. Yeah. Or I just erase it. All right. Conclusion. Yeah. After we do the comparison, the conclusion, algorithm with growth function n log n, yeah, that's our second method. Method number 2 is faster than the one with growth function n squared, the first method. Yeah. So that means we should take method number 2 for this question. Yeah. And here you can see for this algorithm, we do sorting is better than we do not do sorting. Yeah. Question? Yeah.
Where did we get the n squared from? Was that on a previous slide?
All right. Previous, remember we tried to, several steps, ignore some constant, we get n squared. Remember in the previous slide? Yeah. Oh, no. Yeah, because previous, so here, let me just, I need to quickly, yeah, I just moved to previous slide, all right? Yeah, this slide. Okay. All right, look at that. How do we simplify our efficiency function? Let me call efficiency function.
Yeah.
To this one. All right. First, we only keep the dominant term. Yeah. -1 minor term, we ignore it. First step. Second step, we ignore the constant. So we get a growth function n squared. Yeah. Try to make it as simple as possible by ignoring some less important constant. Yeah. Terms. Similarly, this one, because the first term dominates all the other terms.
And we just proved now that why they do, or how they do.
Yeah, now we prove we compare these two growth functions.
Makes sense.
Growth functions. All right, yeah, so that's part B. Next project, yeah, let me discuss, give you a little more information about our programming project. On data part, let me explain the data part. Okay, all right. Yeah. Discussion for project 1. Some more details. We know we calculate polynomial values in 2 different methods. The first one, ordinary method. The second one, Horner's rule. Okay, yeah. But in our implementation, we want to avoid the overflow problem. Remember the last time? Overflow problem. Yeah. Otherwise, if you do not pay attention to this overflow problem, you get wrong answer. The answer is wrong. Okay, garbage, the answer actually. Now, so we need to make sure the overflow does not occur in our calculation. Now, how do we get that? So here I use Java, because for Python, you do not have this issue. Python already taken care of. So you just do it, okay? Yeah, the integer, do it, yeah. So in Java, we need to use big integer class. Yeah. Here, I just take some, constructors, methods, and I want to explain how to use them. Yeah. The first one, constructor, big integer. First, let me explain why when we use big integer class, then the overflow is gone. Yeah. The reason is very simple. Yeah. Look at the constructor here. When we construct a big integer object, the parameter we pass to it is a string. It is a string. What kind of string? Translate the decimal string representation. So actually, you get a decimal number, but you use the string format of the decimal number, not the number format. It's a string format. Okay? Yeah. So here, let me tell you the difference. The string format. String usually we put in a double quotes for string values. Okay? Yeah. But inside our double quotes, we use digits. Okay? So here, I just write some digits. Okay? Double quotes. Yeah. Double quotes, we treat it as a string. So that it has these characters. We treat it as characters, okay, to form a string. Yeah. Not a number, it's a special string. What's the difference? The question is, what's the difference? Difference is big. If you use the number, we know the number, you have to use certain number of bytes to represent number, right? There is a data type, there is a size for data type. For long integer, 8 bytes. 8 bytes for long integer. That's the largest we can use. Largest integer type we can use in Java. 8 bytes. But when we use the string format, do we have any limitation for number of characters in a string? In Java? No. When you use a string as a parameter, you can use any number of characters for a valid string. Any number of characters, no limit. No limit means no overflow. No overflow. Okay? Yeah. We use the string representation, then the overflow is gone. Overflow is gone. Okay? Yeah. Then, how to do math operations correctly, then this Java class takes care of that. You don't worry. So you have this object, you can apply addition, subtraction, multiplication, many different math operations by calling those methods. Underlying strings, underlying implementation, string format, not digit, not number format anymore. That's the reason we don't worry about overflow here. Overflow is gone. Okay. Yeah. So that's the good thing. for this special class. So I want to introduce this special class to you in this first project. And in my second project, I also need to use this one. So I want to introduce it to you as early as possible. Prepare you for the second project. Yeah, otherwise, for the short semester, we may not have enough time for the second project. So I do preparation earlier, okay? Yeah. All right. Then, for the constructor, you need to start with a string representation of a number. And that's easy. So you can do it. 0, when you want to represent big integer 0, double quotes 0. Okay? Represent 1, double quotes 1. Yeah. So then you get that big integer 0, big integer 1, and so on. Okay, all right. So that's the first constructor. Yeah. But the second constructor also useful to generate our data. The second constructor, look at the first parameter number of bits. When we need to generate a random big integer number, we need to specify number of bits. Yeah. Yeah. 2, 3, 10, 100. Yeah, you need to specify a certain number of bits. Oh, certain number of digits. Bits, digits. Yeah. Yeah. Right, bits. Oh, bits. Bits is okay because 2 to that. Yeah. Yeah. Bits is fine. Yeah. Yeah. Equivalent to digits. Yeah. Yeah. Bit. Yeah. So the range between 0 and 2 to that number of bits minus 1. Okay. But the second parameter is a random object. Java random object. You can pass it as the second parameter. What's that random object? What's that random object? Yeah. Because in order to generate a random number, you need a random object to do the generation. Yeah. Here, it's simple. Yeah. This random is a Java class, another Java random class. So you use this random class name. So you construct this object first. Yeah, here let's just use this RND equals, then we call constructor. Okay, we call this Java constructor new random parenthesis. Okay, so after this line, we have a valid RND random object, so we can pass it to this constructor, and then we'll provide the number of bits here. We can get a random big integer object generated following the condition. In this way, I do not need to provide my own method. Yeah, I wrote a method, generate. Yeah, but we have a constructor here, so you don't need it. So you just, use this way. You can generate our random data. Yeah. Because after that, how do we use this random generator? Remember, 2 places we need to use this random generator. One is the coefficients. Polynomial, the coefficients. Second, x, the variable. The variable value, you also use this random generator to generate these 2 places. Okay. Use this. Then use two different methods. Method one, ordinary method, yeah. Addition, multiplication, yeah. Second, Horner's rule. Second method, Horner's rule. Use your big integer. But when you use ordinary method or Horner's rule, you need to use big integer add method and multiply method. Okay? So it's not a plus operator, star multiplication operator, it's not. Okay? So you need to call a big integer object dot add what? Another big integer, right? So you get a value, right? Here, big integer dot multiply another integer value, so you get a big integer with different value. Okay? Yeah. So these two methods, you do addition, multiplication. Okay? Yeah. Then I'll give you the detail, so number of bits, I use number of bits. Okay, yeah. So then the two methods first, they should give you the same answer. But integer, exactly the same, no error. Your polynomial value, there is no error. Okay? Exact number, two numbers should be exactly the same. Yeah. Then the first method, we expect much slower than the second method. Second, Horner's rule, much faster. The first one, ordinary method, yeah. So here I like to control the first method. You can choose number of bits, the number of coefficients. You choose certain number of bits, certain number of coefficients. I like you make your response time of the first method close to 30 seconds. The first one. Close to, not necessarily exact, okay? Close to 30 seconds. Okay? So you can choose certain number of bits and a certain number of coefficients. Yeah. To give you response time for the first method, close to 30 seconds. But that's quite long. Okay. For the second one, then you calculate the same polynomial value. The second one should be much faster. Second one, you compare with the first. If the difference is big or not. Okay, so that's the whole project. Question.
So from my understanding, on the project, we will be constructing two methods, which one of them will be using the regular, and then the other one will be using Horner's rule.
Yes.
And then we're comparing the time efficiency of both methods. Is that correct?
Yes.
And that's after you compile it, right? At the very end, it just tells you the response time, or do you want us to get that from the built-in function in Java?
Built-in function.
The time.
The time?
The time, right? Time, you can find appropriate function, tell you milliseconds. Okay? So when you run this method, start the clock. Then you call the method. After you finish this method, then check the time, take the difference. That's the response.
So
you want an actual 30 seconds?
No, close to.
Okay.
Just give you an idea.
Close to, yeah.
For comparison reason. Yeah.
So how big is the polynomial?
Polynomial, here I do not have idea, the polynomial, at least 100 degree, at least, 100 to 1000, yeah. But another factor control, number of bits, number of bits for your data size. Another factor to control. But here, because I didn't test myself, so I do not have idea of how slow, but I can try on my computer. My computer is relatively slow, because I use it for presentation, so not very powerful.
But utilizing different computers doesn't matter in this case because we're working with the procedural to see the efficiency of the procedural,
Right.
how much time it takes, right?
Right,
So,
for the response time, matter.
the
30 seconds thing, yeah, because on my computer,
the
30
execution
seconds.
is still gonna be.
Yeah, on your computer, probably 10 seconds.
I thought we were measuring the actual procedural
Yeah.
efficiency. Right?
Yeah. So what I like to have between 10 seconds and 30 seconds, that should be fine. More than 10 seconds. Yeah. For the regular method, more than 10 seconds. Because you feel slow enough, right? Yeah, when you wait 10 seconds, you feel, oh, slow enough. But not more than 30 seconds. We do not need that long. Okay? We do not need that long. So at least 10 seconds. The maximum, within 30 seconds. That should be, give you impression, oh, this method too slow. That's enough. But second one, if you do the same thing, a few milliseconds, you will get a few milliseconds.
And you also say that it doesn't have to be on Java, it can be in Python or C++. Right?
Yes.
Okay. But you're just giving us in case we use Java.
Right.
To utilize these
Right.
embedded.
Right.
I don't know if C++, where, like the.
See, how to handle that overflow thing, here I cannot give you helpful information myself. I do not know. Yeah. So actually, I prefer Java or Python. I prefer, yeah, Java or Python.
One way around it is just creating an array and continually expanding the array. and more value.
That's too complicated.
Exactly.
Too
Why would
complicated.
you even do that?
Yeah, so. All right, good. Any question? Yeah.
You're gonna release like a whole,
Yeah.
criteria for the project and
Yes.
so,
Yeah.
are you gonna provide a sample output that you would like us to be
Like
close
how-
to? So that's what we're,
Oh.
at least what I'm usually used to, at least kind of like a sample output.
Yeah, but here I do not, so, yeah, but in my description, you need to generate the result, polynomial value, and the response time. Then, compare. So that's all I need. In my description, I will put it, but I do not show you my result, my response time sample, yeah. Yeah. I like you, actually, I like you, the reason I like you, for different students, I like you to generate different output. Different display, different views, different view. Oh, one thing I did, I will check your code, some students copy the code, yeah, I will do comparisons. Yeah. Every semester I caught 2 or 3 those students. So that's why I like you, definitely. I like you, each student, you show things different. Input, output, all in different ways. Yeah. If I notice 2 students same way, then I will compare your code closely. All right?
So what's the range of like, randomly generated numbers do you want? Do you want like a specific range?
Yeah, in my description, I will tell you.
Oh, okay.
I will put some numbers
For
there.
both the
Yeah.
coefficients and the.
Yes,
x values.
I put some numbers there.
Okay,
But my first version, I just guessed, okay, reasonable. Yeah.
okay.
Then I may do some testing myself. If I feel I need to change, then I will modify those numbers. Here, I do not have idea. Because this version, this class, I changed the first time. The older version, I use floating point numbers. I never use big integers. Yeah, older version. But here, the reason I choose big integers, because I want to prepare you for the second project. So you can do second project because it's a short semester. You don't have much time, so I need to prepare you for the second project as early as possible. Okay, so that's why I modified my old project. Oh, don't go, don't leave. I have big thing. 15 minutes. Let's solve that puzzle question. Yeah. All right. Now this puzzle question. Yeah. Tell me, anyone can do it, can make it? Anyone? Nobody? Because I cannot make it. Nobody. Yeah, so you try, right?
It's impossible.
Impossible.
Yeah.
But question, can you prove it?
Yes.
Yes.
Oh, you can prove it?
Yes.
Wow, that's big. You too can prove it. I
Pretty
like
sure.
you, oh, yeah, I like you explain to me first.
Okay,
I think we have the same method.
Oh, we were
Say, that's good, that only one, you can
Okay.
explain.
so because you have an 8x8 chessboard
Mhm,
and you remove the two corners,
mhm.
they are both white squares.
Right,
That leaves you with 62 points
right,
to cover,
Yeah.
which in theory could be covered by a 31 dominoes.
Good.
But what we discovered when we were looking at it, and that you mentioned that there was gonna be an invariant piece to
Right.
look at.
yes,
Each domino has to cover a black square and a white square.
good,
And because there are 32 black squares and only 30 white squares, that's literally impossible to do.
good. That's. Anybody can understand? Yeah. Let me explain again, yeah. That's. Let me explain again. Oh, in my explanation, I try to emphasize that invariant concept. In your version, yeah, you make it still hidden, so not quite obvious, still hidden. All right. Every domino, because from the shape of this domino, you have to cover two adjacent squares, right? But in two adjacent squares, one must be black, one must be white. You cannot cover two white squares. You cannot cover two black squares. So one must be black, one must be white. Okay, all right. Now I define invariant quantity number in this way. I do definition in this way. So in your version, you didn't say that. Okay. I actually hid it. You use some way, related to that. All right. So here, the difference number. Let's define a number that is number of black squares minus number of white squares. Can we define that number? Okay, yeah. So this invariant, this number equals number of black squares minus number of white squares. This quantity, let's consider this quantity, okay? This must be some number, right? So this whole chessboard, that's 2, right? 32 minus 30. Because 30 white squares gone. Okay? 32 minus 30, right? That number. Think about it. Every time when you use one domino to cover one rectangle, you remove, so let's count. After you cover, let's count the uncovered squares and calculate this again. Uncovered, number of blacks minus number of whites. Okay? Because you take away one black, you take away one white, that difference should be the same, right? Think about it. So you put one domino on it, this number keeps the same. Because you take away one black and you take away one white, the difference is the same. This number is invariant. Okay? Now you put many dominoes. Every time you put on the board, difference the same. Every time you put on board, difference the same. Okay? Yeah? At the end, think about it, the difference. If you can cover the whole board, the difference is zero, right? The difference would be zero, but you know the difference is two. You cannot get zero difference. So this difference, this number is embedded. So you use it to keep track of it. Any way you cover, you can never change this number. Yeah, that's number two, you can never change. But when you have two at the end, you have two black, no white. How can you cover two black and no white with one domino? You cannot. Right? The last step, difference is two. You have two blacks, zero white, but you cannot cover. Invariant concept. Is that powerful, brilliant, right? Yeah, so I read a book, yeah. Once when I travel on airplane, I read a book. The first question is this one. So I like it. I took it, put in my presentations. All right, so that's it. Yeah, let me see. Yeah, although we have a few minutes left, but